Hey, good morning, folks. Um, we've got some opening comments from General Todd, so we're going to get started just a little bit later, right at 10:30. So you're welcome to continue to mingle. Please do. We'll do some. I'm going to do some of this dancing at 10:30, and then General Todd, our Chief Innovation Officer for Army Futures Command, will be here as well. He wanted to talk to you all as well before we got our first panel started, and the first panel started about 10:45. But we'll stay on track for the rest of the time today, and I appreciate your patience. Please continue to meet new people and make connections. Thanks so much.
Got it.
When it's green, that means when it's green, that means you're good. Push this, when it's green, you're good. This, when it's green, you're good. All right, man.
How you doing?
All right.
So you're gonna do stuff with the boss and
Yep.
then everything's
And
good.
then again, walk off.
The white coat? Oh, okay. Cool. There you go, man. It's already on and everything, so you're good to go.
Okay. Hey, folks, we'll go ahead and start taking our seats. For those that are in the back, if I could get you to grab a seat, let's poke the person behind you to tell them to come sit down. We're going to go ahead and get started here soon. Our last day, day 3 for Vertex Energy. I'm really excited to see everybody here. It's hard to keep folks coming for the third day just because people are busy. And when everyone's an important person, it's hard to keep them in one spot for a very long time. So I really appreciate the folks that are in this room today and that came today. We have a fantastic day 3 ready for you. Hopefully the first 2 days were amazing for you. Third day here focused on where operational energy really intersects with that installation management. And so there is a lot of cross-cutting technology here and a lot of great ways that we can collaborate together, because I know there's folks in this room that care very much about like infrastructure. And so I think it's going to be a great session today. We've got 2 panels and a keynote, and then we'll have those breakout sessions. We wanted to have a chance to have Lieutenant General Todd, who's our Chief Innovation Officer, say a few words since everyone's here this morning. That way you have a chance to catch your flight after the breakout sessions and at the end of the day. So we're not trying to get everybody back in here. So Lieutenant General Todd, he's our Deputy Commanding General for Army Futures Command. So, direct line there. And then also the Director of Acquisition and Systems for us. Again, the Chief Innovation Officer, originally an aviator. He possesses an extensive background in helicopters and UAS acquisition for the Army. He loves Chinooks as well. He likes to let me know that for sure. So everyone could please welcome Lieutenant General Thomas Todd. Yes, sir.
Okay, has everybody had a good time? I hope so. I heard what I thought would be the response, which was yay, yay. Well, thanks to AAL and Capital Factory, as well as 75th Innovation. If we could give them a round of applause for putting this on. Not bad for a first try, right? And thanks for creating some energy around energy. Oh, put on, no pun. I know, terrible. But I won't tell Alabama football jokes, which is my team. If you follow football at all. It's an opportunity for us all to be together and really create some momentum, right? This is not just about your individual technology for the Army, right? And you've heard from different speakers throughout the week. Yourselves, you've been up here. You've been able to share and network and collaborate about your area of expertise, what you love, your passion, and that's all great. For us, it's all about really architecting a future, right, that is unmatched, okay? And that involves all of us. That does not involve any of us singularly, right? Everybody has a role to play, but the potential of what we have to do together is much greater, right, than the parts, right? So the sum is greater than the parts in this case. And as we look to see what we can do with energy, right, we have got to, as an Army, begin learning fast. We have to learn to iterate. And I'll freely admit, Perhaps some of the things you've learned here this week was a little bit about others. So you've networked. You probably learned a little bit about other technologies, but you also hopefully learned a little bit about the way the Army works, the way the Army runs, the way we procure things, the way we experiment with things now, which is all new, really at least from the way we're doing it at Army Futures Command. And the goal is to make something together that, again, is unmatched, unparalleled. And we want to do that specifically around energy. So we've taken a couple of focus areas like this to really try and make a difference because we believe they can. I will say that we have opportunities going forward to work with you, but I'll give you a little story of my background with energy. And it harkens back to aircraft development. And, for so many years, we focused on the platform. And it was all about, we just need a new platform, right? To make a difference, we just need a new aircraft. At some point, we had to take an appetite suppressant because, quite frankly, resources are limited. And we had to come to the reality that we have to achieve the same goals without buying new platforms all the time. So now I've moved completely, after being the PEO for Army Aviation that was over all our platforms, to believing that platforms are almost like capital investments. They're almost like facilities. Right? They're permanent. We buy them, right? We have to live with them. Right? The question is, are we going to build a hollow city? I give that analogous to all the 39 cranes around here, right? And if you think about it, the limited budget that we have, taxpayers' dollars that we're going to spend on our investments, they have to make a difference both outside and in. And we've done a really great job of periodically or episodically procuring new buildings like this city is building, or new platforms for our soldiers to live in, operate in, and win in ultimately. But what we have failed to do is iterate quickly inside those platforms with technologies resident in and on those platforms. So if you hear a different business model, it's on purpose, right? Now, how do we do that? Within the policies and statutory guidance as well as regulations that we currently live in. We experiment with you. That's how we do it. So what I would like to do is just say how we work. Really, experimentation is central to how we work. So it's not selling and buying, and I hope you don't take that away from us. Right? There are opportunities here. Make no mistake about it. We will procure things that make a difference. But what we would really love to do with you is experiment with you. That's really what we would love to do, right? We would love to see if it survives operational merit. It might have technical merit, but it might not have operational merit. It may make very little difference. So as we were developing aircraft platforms, we looked at platforms and what we had to do on the battlefield operationally. And we had to lift 6 medevac ambulatory patients off a battlefield with a Black Hawk. We had to carry a squad. The very purpose the Black Hawk was developed was to carry a squad, air mobile, across a battlefield for certain ranges, right? So it meant a certain cargo with a certain weight and a certain range. And you add the environment on top of it. Employ it the way we employ it. And we found that over time, the system had degraded to a point to where we could only carry 2 medevac patients and 5 soldiers. So it not only took 2 Black Hawks to insert a squad, it took 3 now. Right? Operationally untenable. Air assault divisions came back and said, look, we cannot live with that. Right? Medevac companies came back and said, we cannot live with that. So what were they doing? They were stripping out everything they could possibly strip out to make the aircraft lighter. At some point, you reach diminishing returns. So we took a hard look at the Blackhawk fleet, and we happen to have a power source in that Blackhawk, which was a turbine engine. And we said, we don't have enough energy. Where are we missing, right? What we found was we had a transmission that could handle 3,400 shaft horsepower, but an engine that can only deliver 1,000 shaft horsepower. This was a 2,000 shaft horsepower engine. But if you add the environment on top of it, it degraded the engine because of density altitude, temperature and density altitude. So ultimately, what did we have? We had a 3,400 shaft horsepower transmission that could lift a squad or 6 medevac, and we were putting only 2,000 shaft horsepower into it. What's the solution? The solution was, let's see if we can achieve more shaft horsepower in the same form factor, right? Hard enough. And then, oh, by the way, let's not do what we always did, which was reduce range by decreasing fuel efficiency, right? Which is what every engine does as it goes up in shaft horsepower, essentially. You burn more fuel to create more shaft horsepower. Through a science and technology project and an experiment with technology with companies like yourselves, we now have an engine with not 2,000, but over 3,000 shaft horsepower with 15% fuel efficiency as compared to the original engine. 25% fuel efficiency as compared to other 3,000 shaft horsepower engines. So not only did we give them back energy, we gave them additional range. Operational difference. We now carry a squad in that Blackhawk in a high condition, and we now medevac a full 6 patients, which is what's required. We are required to do this. This is not optional, right? And for us to take our eye off the ball and let something like that happen is probably simply we were working on harder things or other things, but the reality is we can't anymore, right? We can't do that. How do we see all that data then, right? Well, we see it through experimentation. That's actually how we are visualizing data, through experimentation. How does that relate to us and energy here? Where's the next system that's underperforming? It's going to cause us, right, significant risk on the battlefield. Where's the next system that could do something that we need it to do if we project where we're going? And this is the beauty of networking. This is the beauty of getting together more than less. So I ask for your help with that. What we'll attempt to do is find the sweet spot with electrification, find the sweet spot with hybrid versus all one solution. We'll be looking for novel, unique, new technologies that are not only capable of performing the mission, but they're actually safe. Right now, I would love to put a battery on a soldier as a platform, and I think you're launching a tactical battery, right, initiative that says, how can we put a battery on a soldier that actually provides the power density, the duration, that's also safe? As you know, if you're in that field, it's an extremely difficult proposition. Right now, a soldier should be carrying 60 pounds. They carry over 100. If you're going to ultimately, put yourselves in the shoes of us, you have to think like that, right? So come experiment with us. Come let us put you with those soldiers. One of the beauties of our Army Futures Command and Army Application Lab is we can give you access to people that you would have never otherwise gotten access to, right? So learn with us quickly. Help us modernize not only the soldier, but all our platforms, all the investments we've already made. And I think at the end of the day, we'll have solutions that we never would have thought we would have had. We'll create and we'll architect an army that's integrated, that works together, right? that ultimately achieves the goals that we want to achieve through our concepts, technology informing concepts and concepts informing technology, that beautiful back and forth, right? That we as linear thinkers often do one, but not both. And then at the end of the day, we have to continually, this cannot be a one-time event, right? What we're trying to do is really start a new culture. And suffice it to say, I think we'll see probably two things come out, hopefully on, I think you have BAA that you'll be putting SIBR initiatives out on for both platforms and soldier technology. I believe one of them soldier borne and the other is UAVs. That's just in the near term. The Vertex website that AAL runs will have other opportunities because make no mistake about it, you've informed us. And the beauty of that is now we can offer to concepts some different alternatives that we to date perhaps did not know existed. Last, I'll tell you that there will be, who knows what the opportunities are, there will be more opportunities. That same engine on that Black Hawk also was the same engine that we use in an Apache. And this is just an example of exponential potential that you don't even know. If you start working on a problem to deliver a squad, you start working on a problem to take care of medevac soldiers, and you look on your left and you look on your right and you start doing horizontal integration. And then all of a sudden, you're not just vertically integrated, you're horizontally integrated. And what did we end up with? We ended up with a simultaneous proposal to upgrade the Apache engine. Right? You may say, well, yeah, it's no brainer. No, it's very hard to upgrade multiple platforms simultaneously with new technology, especially new energy technology, because you are constantly having to make the case why. Already have a brand new engine. Why? 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 What we said to them was if you look at the Black Hawk, I'm pretty sure the characteristics are the same. The environmental characteristics are the same that affect that aircraft as well. Sure enough, we looked at time on station for an Apache, right? To do armed escort of those insertions or those medevacs. And we were losing time on station. We actually had a few occasions where we had to break station, which is in a combat environment is a bad day, okay? It's a bad day because we operate as a team. We do. This is a team sport. And today we're upgrading not only the Black Hawk, but also the Apache simultaneously. Operationally, operations drove that. Here's what happened. The discussion became, okay, we can handle the new energy solution for a Black Hawk. And we said, great, you still won't be able to do armed escort if you don't do the Apache simultaneously, right? It didn't take a lot of operational analysis to figure this out, but it took a long time to make the case, to set aside the resources, to do them both simultaneously, right? So now we are creating a team that is unmatched. And again, we're architecting, right, systems that create capabilities that are unmatched. The next step for aviation as well as ground platforms is onboard energy, onboard power. Because we've done the projections and the growth curves are exponential, right? So they're not linear, okay? We know where we're going with demand signals for directed energy on our platforms, right? Power signals from directed energy to our platforms are exponential. We know where we're going with the ability to operate our network and process the data that we need to process, right? The power draw is massive. And I'll leave you with a last comment. It's a bad day when a soldier has to choose between this energy, this system, or that system. So we have what are called aviation survivability pieces of equipment on our on our platform, aviation platforms. They protect us, they bring us home. Many of the things that you've seen on the news that happen to other helicopters around the world don't happen to U.S. Army helicopters, and there's a reason, right? We have great aviation survivability equipment. They have a heavy power draw, right? Right now, today, one of the things and the only way we know to solve it is just put a bigger generator on board. Right now. But we're looking for really creative solutions to get after what we're about to have to solve, right? So we're trying to get ahead of that. When you're on the battlefield and you and a medevac Black Hawk have to choose between life-saving equipment in the back, right, and aviation survivability equipment, that's a choice nobody wants to have to make. And we go through what's called power shedding right now. And if you've ever had to power shed, it's a significant emotional event, right? And the only reason we had to power shed was because it didn't have enough energy. So choose between life-saving in the back or life-saving the platform, right? Or even simpler, choose between running a processor and doing telemedicine while in route and pumping all that data, right? And survivability equipment or life-saving equipment. We're doing that right now with 30 kilowatt generators, which we shouldn't have to do. So we went to 60, and that's great. And that's a good fix for the interim. First of all, we can't field them that quick. So we've got to do better at architecting the future and staying ahead of, right, the bang. But energy is, to me, the next ones and zeros. Software was key to everything we do, and it is integral to everything we do now. Energy is here, it is now, it is required now. And I look forward to working with each and every one of you. If you ever need to reach out to me, please do. You can reach out directly to me, okay? I am very interested in architecting a future that supports the concepts and then also taking our technologies and helping inform future concepts. But please reach out to me, reach out to Jay, whoever you desire to talk to that has potentially like-minded desires as you do. Experiment with us. And lastly, listen to us, right? One of the things I find is I constantly have just pitches put in front of me. And it's very evident pretty quickly whether you have researched us and you understand our problems we're working on. Now, I would tell you that our problems we're working on are only half the things we really want to talk about, because reality, we'd love to hear things that, quite frankly, we don't even know are potential. So I'm not closed off to the other half. But many times when we have discussions together, whether you be out there on the internet or here in person, please come to us and tell us what you can do to help us solve our problems first. That's a great way to open the door with us, right? Starting the conversation something like, yeah, let me tell you what I've got to sell you is probably a bad way to start with anybody, right? To be fair, but it's kind of funny to watch it go down. I probably have, I don't know, at least 4 or 5 industry meetings every day, and I want to build a relationship with you if you have things that can make a difference to us. And the first step is let's have that conversation. Let's learn quickly. Let's modernize the Army, and let's take energy where it needs to go in the future. So I appreciate the time. Thanks so much for coming. Thanks to the team for putting it on. And I look forward to talking to you, in the future and seeing what we can do together. Thanks. Take care.
Thanks, sir. And for the folks here, we're going to go ahead and roll right into that first panel. We're going to make sure everyone's mic'd up and ready to go. So I'm going to give folks a few minutes to make sure that we've got everything. If you're already all mic'd up, perfect, even better. So I'm going to introduce Dr. Kara Kockelman. So we're going to do charging EVs, home station versus remote. Really, the panel discusses promising approaches to electric fleet management, including where and when to take advantage of remote power generation or mini grids. Dr. Kockelman, Kara, professor of transportation engineering at UT Austin. She is an expert in emerging tech and, regarding city infrastructure and automated vehicles. Her work really focuses on modeling new vehicle technologies and effects to populations in the future, including policy changes, economic situations, and tech costs. Over 200 publications recorded as well. Everyone, please welcome Ms. Kara. Please. Thank you. Let's get started.
Thanks so much for having me down here. This is so fun to be a part of AFC and AEL, I guess. I have amazing panelists here. This may be my first time moderating a panel, actually. I'm used to being in one of those seats, and I'm just delighted how they've paired me with these three guys. So Shashank Shripad on the end there is finishing up his dissertation at Carnegie Mellon. He is a battery expert, so he's in the mechanical engineering department, and really delighted to have you here. So I'll be lobbing a lot of the battery design questions at him. Right next to me is Jorge Elizondo. He has his EE PhD from MIT and undergrad and master's at Monterrey Tech in Mexico. He's won several awards while at MIT, and that allowed him and his co-founder of Hela Technologies to actually recently be bought out by Kohler for managing microgrid distributed energy resources really effectively, recognizing the kind of the competition and the cooperation that goes on with different units feeding into those microgrids. And so it's going to be really helpful to all of us as we hopefully feed back power from our battery electric vehicles. I hope all of you have an all-electric vehicle and then a hybrid. If not, please do make that your next acquisition. So he's got a lot to say on that and being more environmentally friendly as we tap resources intelligently. So we draw more power when wind and solar are high, these kinds of things. And then John Katsoutis comes to us from Illinois Institute of Technology. He's an applied physicist and materials scientist and has this amazing he's done a lot in his career, but right now he's got something called Influent Technology. So he's CEO of that and probably, well, founder certainly. So that is a way to basically pump power back and forth between batteries using a lot of the existing infrastructure. And hopefully in the future that we'll see some cost-effective solutions there, because that's going to allow very fast recharging and special contexts. And so can you tell us a little bit more about that, John? Because it is something that's quite new.
Can you hear me? I have no clue. Thank you.
Did you press the?
I did press it. I just don't know if people can hear me. Yes, I'm green. I'm good. What Influent Energy is presently developing is a new type of flow battery that uses suspensions of nanoparticles to create high energy density nanofluids that could be pumped through the traditional flow battery formats. It allows you to have certain feature sets that don't exist in regular solid batteries. One of them being the idea that you can start treating the fluids themselves as rechargeable, non-consumed electric fuels, where you can imagine that you would have a fuel that can store energy. You can transport it through pipelines, tanker cars, rail cars. The idea of being able to transport energy in a liquid media from sort of a 50,000-foot view is an additional way to transport electrical energy outside of the grid transport. From the fuel side aspect of it, you can start considering the idea of rapidly refueling with a charged fluid into a vehicle in 3 minutes. And leaving the discharge fluid back to trickle charge when the grid capacity is, to the levels it needs to be to start charging it. It just opens up a new paradigm of design space when you start using high energy density fluids in this format. You start looking at the problem set and you start approaching the same type of user experience that you have with any fuel or internal combustion engine, where you run out of gas, you just pump in new gas. The engine produces your power, the gas produces your range. Sort of the same thing, but in the nanofluids, they're never consumed, so they just discharge and you pump them out. So that's basically the context of the technology.
Thank you. Thank you. So all three great inventors here. As many of you know, charging of vehicles for transportation of freight or passengers happens in all sorts of contexts. In the military, of course, it can be abroad and in really undeveloped places. And here in the U.S., you know, energy is pervasive, but drawing power at the rate you might want to supercharge, especially a very large battery, like on some of the electric buses we have here in Austin, or the all-electric trucks we really hope to be seeing, and maybe some electric planes and aircraft in the future is difficult. And the summer is different from winter, and the distances differ, and people's value of time and the commodity that's being transported differs, whether it's, you know, soldiers or, you know, medevac patients or coal, and hopefully not too much more coal, because that really has a terrible health effect. So we really want to get away from that. Just leave it in the ground, guys. Same thing with petroleum, as best we can. So these folks are here to help. And my first two questions, I know Jorge's prepped for these. And let me just call those up. So in what settings will vehicle to grid, so actually protecting the grid so it doesn't stress out and we have another snowpocalypse, things like that, what applications of a vehicle to grid might work well and make some economic sense in the US? I know it's really hard for individuals really to sell back power, and a lot of the manufacturers don't want to see that on their batteries, but it might be something that we're doing in 5 years with city bus fleets. It might be something we're doing in 10 years to protect that grid, especially as we try to get close to 80% renewables in that grid. That's tough to do, but that's what we'd like to see to get to net zeros. So we avoid, you know, more of this climate disaster that's unfolding. And then, you know, long term, maybe that could happen with household vehicles, individual vehicles easily. Do you see that happening?
Yeah, thank you for the question, Cara. And before going there, just thank you for the invitation here. Very glad to be in this panel and talking about, you know, what we know in terms of microgrids and electric vehicles. So going to the question, I think B2G is already here, right? So vehicles can take energy from the grid and give it back to the grid, right? The technology is there. Most vehicles don't have it enabled, but it's just a matter of enabling it. It's a software change, right? And it's inevitable that you know, B2G will come at some point. If you think about it, most people just drive a few miles a day, and they have like 300 miles in their car. So there's a lot of energy that is just sitting there, right? In vehicles, in houses, and you know, workplaces. So tapping that energy that is there is going to be very important if we want to go to make a transition to renewables and be less dependent on fossil fuels, right? So now the question is how we're going to get there, how this is going to scale. And I think since going to B2G, we'll convert these vehicles into dispatchable resources instead of just a controllable load. It will follow a very similar trend as other distributed energy resources, right? And it will be all about incentives. So where does it make sense to implement a B2G? So if we think about where it makes sense right now, it will start in, for example, C&I applications like workplaces where people can drive there and make money while their car is sitting there. Because C&I, commercial industrial applications, have demand charges, for example. So if you discharge during the peak period, you can make money, right? So there's an incentive to charge and discharge. Now, in residential applications, the problem is that it's a flat tariff. So right now, there's no incentive to actually discharge your car. Like, nobody will do it. So now, I think this will change. So even if we start seeing maybe some B2G in commercial vehicles, like electric buses, for example, where owners can convert their asset that is just sitting there into an active asset that can make money. As policy change in the next few years, let's say 5 to 10 years, I think we will see changes in residential tariffs so that will incentivize electric vehicles to charge and discharge to the grid. For example, California right now has already time of use for some residential applications. So if you drive an electric vehicle, you are incentivized to charge it in certain periods and not in other periods. It's still not enough to incentivize to discharge, but I think as things change, this will become more and more prevalent. So I would say in the next 5 to 10 years, we'll see a dramatic change.
Even at $1 a day, like I wouldn't want to, hook up so that they can pay me maybe $1 if they're paying 40 cents a kilowatt hour while I'm parked there for 5 hours or something.
Exactly.
So I don't think that the incentive is that strong in most applications, even in California, where the price of energy is about twice what it is here. So
correct.
Yeah.
I in my case, I have a hybrid vehicles, a plug-in hybrid, and I have a time of use tariff, and still, it's not enough incentive to have to put the effort in charge here, not charge there. Now, if you automate the process with technology, which is also already available, then even if it's just a few bucks a day, it will become more and more common. But it has to be rolled out, right?
So maybe an inductive pad, because I just don't even like the hassle of having to plug in and park in a particular position or something. So
correct.
Okay. Okay. Did you guys have anything to add on that?
Not really, no.
Okay.
I just always thought the bottleneck for vehicle to grid was the cycle life on the battery pack itself. Folks not necessarily wanting to use the most expensive part of the car for, feeding it back to the grid. Correct. And then,
Yeah, it voids your warranty, I think, with the manufacturer. So I'm not doing it.
Well, I mean, it has to be.
We'll have to get past that.
Full industry change, right?
Yeah.
Well, you cannot do it right now. It's not enabled, right?
Yeah, they don't want me doing it. Okay, my next question, also to Jorge, is how can utilities and grid managers best ensure cooperation across EV owners and other privately owned powering devices or battery banks? It might be a second life use of your battery after 15 years or something. The Tesla batteries are lasting really long, like 300,000 miles. They're guessing on those. So that's like double the lifetime of a standard light duty vehicle. But do you see that emerging maybe somewhere else first? Texas is incredibly innovative thanks to our kind of state managed ISO. But
yeah, I think cooperation, it will be also a challenge, and I think it will be more of a challenge than B2G, right? So even though the technology is there and you can have communication, there's two forces at play, right, for cooperation. One is what the end user wants, right? And most people just want to charge as fast as possible. I plug my car, give me as much power as you can, because that's what we're used to with combustion, ICEs. But the other force in play is what the utility needs, right? If we suddenly convert everyone to electric vehicles, the grid cannot take it, right? So we'll have to do upgrades. It will take some time, right? So you need cooperation. So there's this interplay between I just want as fast as possible, and you cannot do it as fast as possible because otherwise it will collapse, right? The infrastructure cannot take it. So that interplay has to be solved somehow. Our philosophy in HELA, and this is what we do as a company, is the end user has the ultimate decision, right? But there has to be an incentive on top of that. So same with B2G, right? There has to be an incentive to, okay, don't charge now and charge later, right? It can be monetary. Mostly it's going to be monetary, but it can also be with information about greenhouse emissions, impact, etc. What we don't like is for an external party to limit, right? Because that will really hinder the adoption of EVs. If you go to your house and then you cannot charge during this period and the utility blocks you to do that, then that will be counterproductive, right? So we believe in letting the end user make the decision. Now, as with B2G, one of the advantages of residential for cooperation is people just drive a few hours or a few miles a day, right? So let's say 20 or 40, and you have 300 in your car. So you still have like a vast majority of your energy there. So you can play with how do you charge, right? In commercial electric buses, for example, it might be more complicated because they will plan to use the entire battery during a shift. So cooperation will require other type of incentive. But in residential, it might be simpler.
Yeah. Well, at my website, we do have a cooperative for the buses here in Austin, and they don't have to give back much while they're stopped. It's just, if you sense the frequency going down in the grid, it's a really powerful protective device, and you sense wind is high. But I do think our grid can handle it, quite honestly. If all of you and all your friends and all your neighbors go out and buy all electric battery, they can't sell them. They're just not enough in the showroom for all of you. But really, it takes about 20 years to turn over the fleet. There's going to be no problem with the grid. We are getting more efficient in every other way. So the utilities would love for us to soak up some of the power that they're delivering. And of course, they are investing heavily in solar and wind because the prices have just dropped dramatically. And in places where you have air conditioning, like we do here in Texas for decades, otherwise we wouldn't really be a big state without it. We've already upgraded all our transformers and things like that. It's up north where we're a little bit worried about those people all getting, EVs tomorrow. So I think we can do it, from what I understand. Shashank, does battery swapping make economic and behavioral or manufacturing or other sense? Because my colleagues haven't really found it to play out. I know Israel and Hawaii might be little islands where you don't go too far, but it's just tough on the manufacturer and design.
Yep. Definitely. If you think about if we take a step back and think about why battery swapping is something that people are attracted to, if you do some rough napkin math and try and see how much energy is actually delivered by, like a gas pump in like a minute, let's say. Most gas pumps pump about 2 or 3 gallons of gasoline in a minute. That translates to about, let's say, 50 or 60 kilowatt hours. If you translate that to the total power that is actually delivered, it's about 4,000 kilowatts. That's, again, without considering how efficient EVs are. Now, if we put that into that math, it's about a mega charger. So pretty much every gas pump we have is roughly a mega charger, right? Now, if we think about the best chargers we can make for electric power, it's about 350, 400 kilowatts right now. That's really the appeal. So with battery swapping, we can basically swap out like a 50 or 60 kilowatt hour battery pack, effectively giving us that energy transfer rate of, like a gas pump. But that is just the promise of it. Now, if you look at the technical challenges, the interoperability, and all of those issues, there are quite a few challenges there, and nobody has been able to make it work. Israel, like you mentioned.
Do you think China might, with like shared fleets, shared autonomous all electric vehicle fleets, for example, or gosh, I don't know, the city of Austin fleets or something like that. Do you think they might be happy enough with a single unit design and want to do it? Or
so, to an extent, at least, the operational issues in terms of consumers not wanting to swap their brand new pack with an old pack and things of that sort of alleviated with that.
Fleet-owned.
So with fleet-owned vehicles, that those issues are alleviated, but still there are issues in terms of the cost that it takes to actually set up like a battery swapping station, which is at least right now about 2 to 3 times what it would take for a really high power DC fast charging station. So there are still commercial and economic issues as well.
Yeah, I don't expect it either. And in the military applications, you don't think it probably is going to make much sense either.
Since I believe the economic and commercial considerations are not as stringent with military applications, there may still be a case for battery swapping, I believe, if the technical issues and operational issues are not as much.
Got it. And I don't know if you guys wanted to add anything there.
No, I think it's quite interesting that the amount of power that is delivered in a pump, right? And you can do it in 12 pumps at the same time.
Yeah.
And then 85% of it is wasted as heat. So.
I was looking yesterday that the amount of energy stored in a gas station in the tanks below is in the hundreds of megawatt hours. So that's larger on par with the largest battery that has been installed. So it's quite impressive the energy density you can get from fuel, and it's going to be a challenge to change to batteries.
Yeah, but we changed from wood, and dung in most countries, and yeah, we can do it again.
Something with more energy density.
Yeah, those dinosaurs, but we can leave them be. Maybe some future generation will really need them, but we don't. Shashank, another question for you. What are the economic and other limitations on fast charging, and what would be the price of like DC fast charging, especially for a very large vehicle on a long distance route, like a heavy duty truck on a 500-mile delivery.
Yep. Again, going back to that napkin map we were doing, right? Actually, what matters from an energy storage, at least electrochemical energy storage standpoint, is not the absolute amount of power that's delivered. That's obviously important for the infrastructure side of things. But for the energy storage device, it's more of the power normalized by energy. So effectively, the time it takes to charge that particular energy storage device. In that regime, about 10 to 15 minutes is where the best batteries currently can do. And if we look at the amount of power required to, let's say, charge an electric truck that can do 500 miles, you still need a mega charger. And having a mega charger with more than one truck brings up all of these issues of demand charging and things of that sort. And when we think about the commercial feasibility of electric semi-trucks, it's always this sort of trade-off between the operational cost savings from using electric powertrains versus diesel powertrains, and how quickly that payback period is achieved. And the electricity price plays a huge role there, obviously. Of course, this is predicated on what the gasoline price or the diesel price is. But somewhere around 20-25 cents from what we've seen is where things start to become less straightforward for electric semi-trucks. And the economic case is not as clear. So being able to deliver that megawatt of power and also at less than 25 cents per kilowatt hour is really the crux of the challenge there.
So that's going to be really difficult because that's less than what Hawaii pays, and it's about what Californians pay at standard trickle charging, for example. So I could see it being, $1 per kilowatt hour pretty easily. And do you think there's always going to be batteries on site for that, or they'll be able to deliver to multiple trucks off of high voltage lines in some parts of Texas, for example?
Yeah, that's a great point. So with batteries on site, again, that starts to add cost to that equation. With high voltage lines, I think there is definitely a possibility to build something. But again, the infrastructure costs are not very clear because nobody's done it at scale or in any reasonable installation.
But yeah, now's the time with the Dieselgate and this Investment and Jobs Act. We're rolling out a lot of money in a lot of stations, not just to help the passenger vehicles, but the heavies. But it may be that the best application really is the depot charging of the single unit sort of delivery vehicles for last mile rather than the long distance. But we'd love to see it. Again, diesel is really, really dangerous, and it should be taxed more heavily than gasoline for sure. It's killing, I guess, the fine particulate matter from coal and diesel in this country is killing about 100,000 people early every year. It's about 5 years early is how much earlier those people are dying from the long-term inhalation of our air, which seems pretty clean to me, but unfortunately, it's not as clean as you would think. Okay, so moving on to John, what are the three most, this is a very tough question. He was up at 3 a.m. Giving this some good thought. I'm so sorry, John. But what are some reasonably, long-term, possibly cost-effective, or even in the near term, what is the most likely case for alternative energy storage out there for remote charging in places like rural United States, although you can go anywhere in this country now with a Tesla.
Africa versus Asia.
Yeah, just to take one. Don't worry, it's not a test.
Yeah, so I got this question posed to me. I'm not an expert in this particular question. I can tell you the combination of things that I would consider when we're talking about remote charging. Obviously, you touched on the big one. What does the local infrastructure look like to it? And then it turns into a collage, right? So you can have the direct high voltage lines going in, but maybe you don't have access to good power. So then you've got to bring on energy storage. Well, which energy storage are you going to bring on? Is it going to be, this technology or this technology? Well, right now there's supply chain issues, right? With lithium ion, we're hearing about this, right? So costs go up. And then, okay, well, in what location? Well, guess what? Yeah, obviously batteries don't do as good in cold locations. You're going to need to address that. And so when you sent, that question over, at 3 a.m., I'm like, this is an entire collage that is specific. There is no one answer to any of this. It's hyper localized. It's dependent on the environment. If you're in Africa, are you going to have access to grid locations? No. Okay. Well, now you have to talk about renewables coming online that are going to be supplying that power. In the United States, there is actually a lot of a wider span of opportunities, right? Because we have a more advanced grid structure compared to Africa, but is it closer to a city if it's in rural? And it just, from my perspective, it just turns into this almost unmanageable type of problem set. So there is no good single answer I can give you on the top three.
Right.
It's a matrix.
Right. But they could bring in a battery and they could bring in a turbine, maybe depending on the wind conditions and depending on the latitude, they could bring in some cells.
Yes.
And so, but would they ever bring in your technology and Fluid?
So the way we look at our technology is it is a way to transport electrical energy outside of a grid structure. And there are technologies like things called cured in place pipes, where you can retrofit pipes with polymers. They do it all the time. And you can set up the same distribution routes if you're creating a separation of energy storage and power, where your energy is stored in a fluid, right? Then the vehicles themselves become the transport. You leave it when it's discharged at that location for someone else to take maybe a little bit later when they come through. So it becomes sort of a self-organizing type of distribution just by utilization of using the fuel itself. And so that additional capacity is where I think potentially there are solution sets that can be brought online that are unique to addressing the infrastructure issues, as well as the rapid recharging and refueling issues. And then there's also something nice about having competition, right? And those forces that then begin to create sort of the self-moderating stasis of balance for the development of rapid recharging. At least that's how I look at it.
Yeah, and this question takes us into that last one, which is more, a U.S. military application and, rapid and remote. Like, what would you recommend for electrified transportation abroad?
I heard a lot from the breakout sessions and listening to the military folks. So from the 50,000 foot view, in my head, there's four. From what the pain sounds like it is, they need to have rapid refueling. Okay, so we need to talk about fuels. So there's hydrogen, and it's still in the works, you've got CO2 reduction to methanol, right? There's high energy density flow batteries, regardless if it's specifically what I'm working on or other groups are working on, hopefully mine. And then just JP8. I mean, what you guys are using, right? The one thing that they all have in common is this concept. I keep saying it, is this separation between energy storage and power. They all have that in common. Okay. And that's why they're attractive, because when you separate the energy and the power, you can get rapid refueling. You can design your power system specifically to meet the max power loads that you need, independent of your energy storage. That's a powerful thing. Okay, now go down the next list. Nobody likes fire, right? Our DARPA PM put together a talk, and there was something that caught my ear. I've heard it before, but for some reason it really stuck, that most soldiers survive the initial attack. They die in the fire and the smoke that follows. Well, okay, that takes out, let's talk about it, the JP8, that's flammable. The hydrogen, it's explosive. The methanol, if you did it. So now we have to look at aqueous chemistries. Those are non-flammable. This is the driving mechanism behind our work. This is what we are trying to go after. This is what we are working towards. So I say it jokingly, I hope it's my technology, but any aqueous-based concept that can separate energy storage from power rating is the one that I hear checks the boxes. Then you go down the next one, the materials you make it out of should be from a vertical supply chain that exists in the United States, something that we completely control ourselves. And then that leads you down this material matrix of, well, what are those? And there are chemistries out there that are on that palette. And so that's the checklist. And that's how I see the answer to that question.
Great. Anything anybody wants to add up here before we break into the audience questions?
I just want to mention that I think the separation of power and energy is key. So I agree a lot with John there. And we have done projects with hydrogen where you have that separation, right? And it's very, very convenient because you can scale them differently. So you need more energy, you just scale the energy part. You need more power, you just scale the power part of the battery. So definitely a very important concept.
One quick point, especially with regards to remote charging and perhaps to an extent the energy efficiency of most of these operations that may be interesting to consider in this conversation is the use of energy harvesting. Because with a lot of these operations, there are heavy mechanical loads involved. So there are a number of concepts using things like piezoelectrics coupled with, again, electrochemical energy storage like supercapacitors and things of that sort, where you can eke out maybe 5%, 8% energy that can extend the operational, time of some of these operations by a little bit.
Super, super. So I really appreciate the 4 questions we've got here. Feel free with the QR codes, I guess, on the back of the chairs or something, to send in a few more here. We've got about, I don't know, 5 minutes left. Is that right? Okay. So Harry, Maloney asks, how does the panel feel about the utility of electromechanical storage systems like a Flywheel, carbon fiber?
I can comment that typically those are for shorter durations. Like a Flywheel is very good for like frequency regulation to the grid because it can give the, it has a lot of leakage, but it can store a lot of energy, right? So it's an interplay always with how much leakage do you have in your storage element and how much efficiency you have to process from one side to another. So Flywheel and those kind of applications are good for short duration from what I've seen.
Of course, the embodied energy of anything is always a consideration. So when you do buy an all-electric vehicle, about half of the lifetime emissions and energy of that vehicle is at the start in the manufacture of the battery and the vehicle itself. So don't crash it. Otherwise, you're not going to beat the ICE. Here's one from Michael Callender. What are the technical challenges of using underutilized heavy-duty EVs? So these are heavy-duty trucks, I guess, as backup power during, or maybe buses as backup power during grid down situations. And of course, we were talking about this. I'm planning to do this at my own house. We also have like a gas storage tank because we're off the gas grid, unfortunately, in my neighborhood on site. And so there are ways, to protect yourself, but also hopefully the grid and the incentives to do that. I really hope will be there, especially in the municipally controlled utilities, which we have here in Austin, thank goodness. And we do not have them out there enough. They really do a great job, much better than the private sector, I think, of getting the right behaviors and getting the right feedstocks into their contracts. But yeah, if you guys want to talk about that a bit more, the technical challenges, I think you might want to answer that one, Jorge.
Sure. I mean, I can make a couple of comments. I think technology-wise, we can do it right now. It's just about what John and Kate said, like the manufacturers don't let you do it because it voids warranties and things like that. But technology-wise, you could just plug your house into your car. And I think the new car, the Ford electric truck is coming with that capability. So the capability is there. You do need to disconnect from the grid because otherwise you need interconnection permits and things like that. But if there's a blackout, you can just put a transfer switch there and operate your house from your car as if it was your stationary storage. Not all manufacturers will allow it immediately, but I think it's something that will come.
Yeah.
Especially with underutilized electric semi trucks, which have, let's say 800 megawatt hour, 800 kilowatt hours or megawatt hour of energy storage. They could even be used as sort of distributed charging stations, especially if with concepts such as the Ford F-150 electric.
Yeah, and I think California is experimenting with moving around big batteries, like in fire-devastated regions, and to kind of, PG&E has had a lot of problems, so they are doing that. We're also thinking about that for our shared autonomous all-electric vehicle fleets here. Is instead of investing for sure in a property to have all your power and your lines to inductively charge that fleet, that driverless fleet, is to actually move the banks around as the fleet expands. So I think, but they also can give back, especially in critical situations, and hopefully socially, not just to protect your own household, as attractive as that is to many of us. John, Chris Venturini asked, what are your thoughts on using a non-aqueous solution to separate energy from power?
Yeah, you can do it, but now you're dealing with flammability again and explosions, but you do gain on your stack size, right? Because your voltage can go higher. For military specific, I think removing military specific and aerospace specific, removing the pain point of flammability and explosion is the driver. If we're talking about civilian applications, you potentially will win there, and I hope you don't. But yes, there's definitely potential there.
And then I think we have time for this last question from Jacques Villeneuve. Any comments on the use of metal air technologies for remote power generation and storage, like zinc air and aluminum air?
I guess there are a number of interesting concepts, especially with the advent of concepts like ion air and so on, which are lower on the energy density or specific energy metric, however, can be installed at fairly large capacities well enough.
Oh yes, removing the cathode and upping your energy density, just playing that game of using oxygen instead. Yes, across the board, you will gain. Your costs will go down. I personally believe that metal air has got a very, very strong future. As a matter of fact, Form Energy is doing iron air. They just did a 200 million D round, I think. Yes, I mean, just big yes, exclamation point.
Fantastic.
Hey, yes. Yes.
So this reminds me, at UT, we did have a Nobel Prize in Chemistry given to John Goodenough just a few years ago, and Ram Mantharam runs that unit. So we do have a lot of battery work being done there. And later today, you have a chemist from UT moderating a panel on a related topic. And then after that, I think you have a professor of mechanical engineering, Luis Sentis, also moderating a panel of amazing technologists. So we're really lucky what you guys are doing here, bringing together industry and recent graduates and everybody with amazing backgrounds to try to move this world forward. So thanks for your time, everybody. I hope you have a great lunch.
Thank you. It was nice meeting you.
Thank you.
Okay, hey, just real quick, we're doing lunch. I know everyone wants to go, so we can get back on time for a 12:30 keynote. I hope there's some discourse. Right? That's exactly what this is about, like differing opinions on how we do something. Because we're going to talk with Levi Tillman, VP for Policy and International Outreach, after we get back from lunch, and he's going to talk from Ample on battery swapping, but also kind of the state of electrification in an international sense as well. So look forward to see you at 12:30. Please come back 12:30 in the seats. Thanks so much.
push this button when it's green.
All right.
You're good.
Hey, folks, for those that are just coming in and then online as well, we're going to start here in the next couple of minutes. I'm going to try to make sure we wrangle up the folks from outside, get them back sitting down again. I know it's a hard 1 hour lunch period, so we'll get started here in a few minutes. Thanks. Okay. Hey, folks, come on. Let's sit in our seats. I'm excited to get started here just a few minutes after 12:30. Let's get into the chairs. Very exciting. Hey, so we've got a great keynote speaker here and a different perspective for sure. Levi Tillman, VP for Policy and International Outreach at Ample. He's going to speak to technical insights on battery swapping and the state of electrification with our near-peer competitors and how battery swapping can improve operational flexibility, speed, overall economics of electrification, both in civilian and military applications. Levi is a former member of the Obama administration's Department of Energy. He's been a senior advisor to Valnex Strategic and currently leads global policy for Ample. He's led an initiative on decarbonizing manufacturing, use phase, and end-of-life emissions at the World Economic Forum. Fantastic team player, Levi, and can speak about a half dozen languages, like 6, 7, 8, something like that. So a round of applause, please, for Levi. Oh, yeah.
My shaking hand is out of commission right now. Well, first of all, thanks everyone for having me here. This is really exciting. I don't actually get to spend a whole lot of time in the defense world. And so I got in last night, have been hearing some different perspectives. At the happy hour, someone told me that on the first day, people were casting shade on battery swapping. And I was shocked. I said, don't tell me that that's so. But today I got a taste of it for myself. So I'm excited to disabuse all of you of those terrible things that they said about our technology. But I want to start and preface this by saying that we are mostly focused towards consumer markets right now. And actually, we're more focused on B2B markets. So some of this may be applicable to military settings. A lot of it probably won't be applicable to military settings. But what I would love is if you think about what we're talking about and think about how it could be applied to make your forces a better warfighting machine. So let's start with the basic layout of the electric vehicle market in the United States of America. The problem with scaling electrification from where we are today to where we need to be in 10 or 20 years is that most electric vehicles don't have access to home charging. They don't have a dedicated charge point. Let me just ask the audience a few questions. How many of you own an electric vehicle? Raise of hands. All right. 1, 2, 3, 4, 5, 6. How many of you own an electric vehicle, but you don't have a place where you can charge it at home? No one. Okay, that's me. I'm the only one. So if you have used an electric vehicle and you don't have a place where you can plug that thing in overnight, where it's sitting 95% of the time to charge, you realize that today's public charging system is wildly inadequate. Here in Texas, most people do have a garage where they can plug in their electric car. But in San Francisco, where I live, or in Denver, where I grew up, that's not necessarily the case. I've lived in half a dozen houses, condos. We've always been street parking, or I've been parking in a public garage where I couldn't plug in that electric vehicle. So for the affluent suburbanite who can buy a Tesla and who can plug that vehicle in overnight, charging is a great solution. And the reason is you hardly ever have to use that public charging infrastructure. But for everyone else, swapping is a good bet. So let's talk a little bit more about some of those market segments that swapping applies to. If you live in a multi-unit dwelling, if you park in a public garage, if you street park, or if you're a fleet where you're going to have to be repowering a lot of vehicles at the same time, and you need to install the charging assets to do that, then swapping is a really good solution for you. From a grid standpoint, swapping also makes a lot of sense. The electrical system works kind of like a market. Supply always has to meet demand. And when you flip on a high-powered charger, that's like flipping on a large commercial building. Now we're talking about having to install hundreds of thousands of these things across the United States. There is a study by the Boston Consulting Group that said every electric vehicle that is added between now and 2013 is going to require between $1,700 and $5,800 in grid investments for charging capacity. Now, the scary part of that is that when you look at the expansion of the electric fleet, there aren't economies of scale. There are diseconomies of scale. The higher that penetration goes, the more we're going to have to invest in the grid to be able to take care of that public repowering of electric vehicles. And all of that means that if we want to go from a system today that is, really niche, about 0.5% of vehicle miles traveled in the United States today are electric, to a system where every Toyota Camry, where every F-150, or every delivery vehicle can run on electric vehicles, we're going to need some different solutions than the ones that got us to 0.5% electrification. So a good model for where the market is going is China. Now, I'm not sure if you can read this slide, but to me, the lower left-hand corner is very instructive. That is a graph of all of the DC charging installations in the world. That big blue block is China. China has more than 80% of the world's installed base of DC fast chargers. See that little orange block up on the right-hand side? That's the United States. We have about 5% of DC chargers installed in the world. And so it's instructive that China, which is probably about half a decade ahead of us in terms of electrification, they are now investing very heavily in battery swapping. And it made me laugh hearing the last speaker saying that battery swap has not been deployed successfully in the world because it is deployed at massive scale in China. China now has 1,600 battery swap stations. That may not sound like a lot, but it's the equivalent of about 160,000 100-kilowatt fast chargers, which for any of you who don't keep track, that's about an order of magnitude more fast chargers than we have in the United States. We have about 20,000 DC fast chargers in the United States. So why are those battery swap stations so powerful in comparison to a DC fast charger? There are a couple of reasons. The smaller reason is they tend to be pretty high powered. So you have at minimum probably 300 kilowatts coming into them, but some of them have a megawatt of power coming into them. So they're bigger. But more important is the amount of utilization that you get out of that really expensive connection to the grid. So I'm from California. We have a lot of DC fast chargers installed along the highways, but on average, they get 3% utilization. With a battery swap station, the whole thing is filled with batteries. That means you can get effectively up to 100% utilization. That means that a similarly powered battery swap station is going to get about 30x utility as your 100-kilowatt fast charger. So that's a much bigger reason why those 1,600 battery swap stations are it is a larger asset than you would think based on that relatively small number. A lot of you may be familiar with the company NIO. They're sort of a pioneer in the battery swapping space, but it's not just NIO. Basically, every single Chinese auto manufacturer is pursuing battery swapping, and the Chinese government is all in on this. They rejiggered their EV incentives recently so that battery swap-enabled vehicles are preferentially subsidized, and the Chinese realize that if they're going to meet their electrification goals, they just have to have something that is as fast, as convenient, and as economical as gasoline. If you don't do that, you're not going to be able to make the transition to electric vehicles. So one automaker, NIO, already has 900 battery swap stations. That's the equivalent of about 80,000 fast chargers. That's 3 times as many fast chargers as we have in the United States of America. Their plan is to deploy 4,000 battery swap stations globally by 2025. China already has, actually, if you go back and you look at announcements from the various Chinese companies that are installing battery swap stations, they will have the capacity easily to power 100 million electric vehicles off of battery swapping by the year 2025. And America is way behind on all of this. Ample, my company, we're the only ones in the game here. But it's not just China. Battery swap stations are being rolled out now in Norway. Next will come Germany. And India has recently made an announcement that they've surveyed the EV charging landscape. They've realized that the power constraints and the space constraints mean that electric vehicles just won't work for India if they're based off of this model that the United States has pursued, where you have to have it plugged in 95% of the time, where you need to have an electrified parking spot. So India is also pursuing battery swap as their primary mode of electrification going forward. So that's 2/3 of, that is the 2 largest companies in the world two largest countries in the world, excuse me, that are focused on battery swap now. So this is what a battery swap station looks like in China. What strikes you as being different from a standard EV charger? Anyone? It's drive-through. It's very large. It's very large. That means it's very expensive. These are large industrial facilities that are filled with heavy robotics that are really expensive because they need to be able to swap a 1,000-pound battery that's extremely delicate. Ample, my company, has a different approach to battery swapping. And it allows us to deal with some of those constraints of size and geography and also access to power. We take that 1,000-pound battery and we break it down into smaller chunks that you can mix and match and stack like Legos. That means that they can fit into any vehicle, any form factor of vehicle. The way that we accomplish that is we have an adapter plate. You can see on the upper right-hand side of the slide, an adapter plate that fits into the cavity of the electric vehicle where the battery would otherwise fit like a glove. For all intents and purposes, the car doesn't know whether it has its battery installed or adapter plate installed in it. Then below that adapter plate, you'll see some trays, and those trays are what hold our modular batteries. Those trays are what plug into the vehicle and unplug from the vehicle. The plate and the trays are custom designed to the vehicle model, but those modular batteries, they can be used in any electric vehicle. And that means we don't have to deal with the inventory problem that is typically considered a big challenge for battery swapping. On the lower left-hand side, you can see our swapping robot. It's a little bit small there. And on the lower right-hand side, you can see our swapping pod. And this is what an ample swapping station looks like. The fact that we have these smaller modular batteries allows us to have a much smaller, much more economical system that can service any electric vehicle which has an ample adapter plate installed. What that means is that we can work with existing electric vehicles. You don't have to redesign the electric vehicle in order to utilize an ample swapping station. Our battery has a layer of power electronics over it that can manage the power characteristics. And what that means is that even if a vehicle is designed to run off of a different voltage than another vehicle, our batteries can handle that. And finally, we don't have to do any construction. The thing goes up like an erector set. It's very quick and easy to install. And on a vehicle per vehicle basis or charge by charge basis, it's actually much more economical, much more cost effective than charging is. So if you go down the list of characteristics that consumers and operators care about with respect to electric vehicle charging, battery swapping performs extremely well. It's fast to fuel. It is lower cost than gasoline. It's lower cost than public charging. When you buy an electric vehicle, one of the big challenges is that that battery wears down over time. But with a battery swapping system, you don't own that battery. You lease the battery. And what that means is your battery never degrades because you're operating off of a shared pool of batteries. Our system is very fast to deploy, and the customer experience is exactly like gasoline. It's a lateral transition, a seamless transition from what we're all used to in terms of gasoline refueling. For the grid, rather than it being a liability, it's a huge asset because you have these big banks of batteries that can absorb renewable energy when it's produced and dispense it very quickly when it's needed. And then finally, we can just refuel a lot more cars per kilowatt hour of energy or per kilowatt of energy delivered to the battery swap station than an analogous charger can. So I haven't done a lot of analysis on how this would fit into a military context, but there are a few characteristics that stand out to me as being potentially important. First of all, vehicle uptime. When you plug in an electric vehicle, you lose the ability to operate that vehicle for as long as it takes that vehicle to charge. That is the loss of an incredibly important asset. When you swap a battery, that vehicle is back in commission very quickly, within a few minutes. You have the ability to run a microgrid off of your battery swapping system. And you can utilize those batteries, you can utilize the energy that you're producing much more flexibly by adding that additional degree of freedom into the system, not having to be connected directly to the vehicle. Renewables, frequently don't produce as much power as a fossil fuel-fired power plant will. What that means for a battery swapping context, though, is that we can absorb that power when it's available, and then we can dispense it really quickly when it's needed. And finally, you can actually vary the capacity of a battery pack in your electric vehicle. So if you know that you have a vehicle that is only going to be out on a 20-mile circuit, you put 50 miles worth of batteries in that vehicle. But if you know that you're going to be on a 200-mile circuit, put 300 miles of batteries within that vehicle. So it's a much more efficient use of batteries at the end of the day. You can match the capacity of that vehicle to its duty cycle. So I would love to answer all of your questions about battery swapping. I would say that anyone who doesn't think that battery swapping is going to be a big part of the future of electric vehicles hasn't followed the market. They don't know what's happening in China. They think that America is still leading in this space. Unfortunately, we're not. We're a distant third. China is leading, Europe is second, and America is catching up. And the first two, they're all in on battery swapping, and we should be too. So why don't you come up here and we can do some Q&A and hopefully disabuse people of some of these misconceptions about battery swapping.
That sounds wonderful. Levi, thank you again for your take on battery swapping here. Our first question is whether China has standardized on battery types between manufacturers, or are the swap stations manufacturer specific?
Yeah, so not yet. There is a standardization process that is happening in China, and it's going to be interesting to see how that works out. You have some Chinese companies that are now copying what Ample is doing. So they're looking at a modular approach to battery swapping. But up until now, it's been a custom build. So NIO has their own battery pack design. That's one of the leaders in battery swapping in China. Geely has their own battery pack design. They all own and operate and run their own battery swap stations. And in China, that kind of works because China has a history of regionalization in their electric vehicles, and not just electric vehicles, in their vehicles market. Volkswagen was one of the early manufacturers of vehicles in Shanghai. And the Shanghai government made a law that taxis had to have a certain displacement of engine. And lo and behold, Volkswagen was the only company that manufactured vehicles with that displacement of engine. And so all of the taxis in Shanghai ended up being Volkswagens. And China does this a lot, this kind of regionalization. So you can have a manufacturer that's relatively concentrated in one region that can deploy their own infrastructure in a way that is not as easy here in the United States or in Europe. But yeah, no, they are not standardized at this point.
And kind of follow-up question there. What do you think the US's approach to battery differences between manufacturers should be? Should we, from a policy perspective, try to make batteries interchangeable, or do you think it's a kind of the opportunity for third parties such as Ample to fill that gap?
Yeah, that's a really good question. I don't think that we're at a stage where it makes sense to start regulating these types of standards. But what the US government can do is they can say, this is a strategic priority. Battery swapping is a strategic priority. We're going to invest in this. We're going to support companies that are investing in this and support fleets that are utilizing battery swapping. The whole EV market, this entire process of electrification has been policy driven. This is not something that grew up organic from the market or from the labs of MIT or Stanford. This is something where a bunch of policymakers got in a room and they said, we want to deal with air pollution. That was the first goal. And in order to do that, we need to eliminate emissions from vehicles. And it started in the state of California. They told automakers that they had to slowly build more and more electric vehicles if they were going to be allowed to sell electric vehicles and non-electric vehicles in the state of California. So electric vehicles were kind of the price for admission to the California market. So this is a policy market. It's still a policy market. It's starting to have its own legs. But if you look at hydrogen, if you look at battery swapping, if you look at these different early stage technologies, none of them succeed on their own 2 feet. They all have to be shepherded into the market by policy. And that's just, that's how investment in these kind of long range, heavy industry sectors works.
Well, that's an interesting segue. Our next question is looking at outside of car, truck, and vehicle platforms. Do you see this type of battery swapping technology having application to platforms like trains and like that sort of platform?
Yeah, so I don't know about trains. What I can tell you is last year, the first quarter, like 30% of all heavy duty electric vehicles that sold in China were battery swapping electric vehicles. So definitely big application in the medium and heavy duty space. It makes an enormous amount of sense. You don't want to have that big, expensive asset stuck charging for hours and hours at a time. The amount of energy that is required to power these devices, you know, you can't charge them that quickly, right? And so you don't want to take that offline. And battery swapping is a really good solution to that challenge.
Thank you. We've got a couple questions around battery ownership in a battery swapping model. Can you talk a little bit more about the business mechanics of leasing batteries and how you think that will play into rapid advances in underlying battery chemistries?
Yeah, so one of the fundamental components of a battery swapping system is you don't own your battery. It doesn't work if you own your own battery. Tesla tried, you know, I mean, you can hardly say they tried, but they sort of dipped their toe into battery swapping about 8 years ago. They did a horrible job of it. And probably one of the biggest mistakes that they made, in addition to only having one swap facility, which, you know, one swap facility is not going to get you very far, is they wanted you to still own your own battery. And so you would have to make a reservation, go to the swapping station, swap your battery, and then come back for your battery later. That's kind of a crazy idea. People start worrying about, am I going to get my own battery back? Like, you know, what if they give me another battery that's inferior? The only way that battery swapping works is if you do it on a leasing model, where you say, look, you pay a battery as a service fee for access to use a battery, but you don't have to buy that battery up front. And what that does is it actually significantly reduces the cost of the vehicle. So you might pay $22,000 for a $30,000 vehicle up front, and then you pay a monthly fee of $100 to utilize that battery. The way that we work is you pay a fee to utilize that battery on a monthly basis, and then beyond that, you pay for every kilowatt hour of electricity that we deliver to that vehicle. So we don't sell swapping stations. We sell miles, and that's how we make our money. The battery rental fee just covers the cost of the battery. But what it does is it dramatically reduces the upfront cost of the vehicle for the consumer, and it allows you to transfer that CapEx into OpEx, which is very attractive for a lot of companies, maybe for the military, I don't know, but certainly for a lot of lower income consumers.
Thank you. We've got a few more questions that are popping in around the intersection of the battery swapping and OEMs, particularly around roadmaps for EVs look like they might include batteries included in the chassis or structural components of the vehicle. And some OEMs are starting to include like proprietary power management systems. Do you think these are like fundamental threats to battery swapping?
So yeah, I mean, this system is not going to work if the batteries are integrated into the chassis. That said, integrating batteries into the chassis is a terrible idea. I mean, how many of you guys have an iPhone? How many of you have an iPhone that is more than 3 years old? How long does that battery last? Not long enough, right? And if we're doing that with our vehicles, that's a real problem. Now, the benefit of battery swapping is you're not going to get a shorter and shorter range as the years go on. You're going to get a longer and longer range. The reason for that is that battery chemistries are going to improve. They're going to be more energy dense. They're going to be lower cost. And so your 5-year-old iPhone will have a longer battery life than your 3-year-old iPhone would. And so that's a huge benefit for consumers.
Thank you. I really appreciate that. And we've got maybe time for 2 more questions here. Do you have to look at new vehicles? Do you have to look at new vehicles that manufacturers are building to build a future for battery swapping, or can current EVs on the market use your system?
So the way that our system is designed, the manufacturers don't have to redesign their vehicle at all. Almost every vehicle on the market operates on some version of a skateboard platform. And what that really means is you have something that looks like a skateboard. There's a battery pack that is bolted to that skateboard. And what we do currently is we just drop that battery pack out and we install our adapter plate. And that's what our batteries plug into. Going forward, we're going to be working with OEMs to have those adapter plates installed on the line. And if you're a fleet that wants to run a bunch of electric vehicles, rather than paying for the really expensive installation of charging and having to manage those assets, you'll say, I want a battery swapping vehicle rather than a charging vehicle. And let me just give you a sense of how much it costs to install EV charging. A level 2 charger that takes 4 to 16 hours to charge your electric vehicle, the average level 2 charger in California costs $18,000 to install. And it still takes at least 4 or 5 hours to charge your electric vehicle. A DC fast charger, which the fastest DC fast chargers in San Francisco, where I charge my electric vehicles, they take about 45 minutes to get me about 60% charge. The cheapest ones cost about $50,000, and that one is going to take 2 hours to charge my vehicle. The most expensive ones are over $400,000. There's no business model there. I pay the equivalent of $7 to $20 a gallon for charging my electric vehicle on a regular basis at a public charging location. And all of those public charging companies are still losing money. Now, some people will say, well, Tesla public charging is cheaper. Yeah, there are two kinds of public charging. There's subsidized public charging, and then there's really expensive public charging. Both of them lose money. And so, you know, whenever you're thinking about what does this future look like, is it going to all be charging based? You need to really understand the fundamentals of the current business model and the fact that, you know, there's a lot of stuff there that just simply isn't worked out. Who's going to pay for all of the generation, all of the transmission, all of the distribution capacity that's required when we're flipping on these 1 megawatt chargers that would be required to, you know, charge this 5-minute battery that, you know, theoretically might exist sometime in the future? It's not feasible. It's too expensive. So there are going to be a number of different approaches. For people like me that live in an apartment, you're going to have a battery swap vehicle. For fleets, you're probably going to have a battery swap vehicle. For high utilization vehicles, you're going to have a battery swap vehicle. For affluent suburbanites who can plug in overnight, you're going to have a charging vehicle. Why? Because you hardly ever have to charge in public. So $7 a gallon electricity, it's not that big of a problem for you.
Thank you. I think that's it for our questions. I'll leave it with this comment. Actually, we've got several comments that are along this train. There has been some shade thrown at battery swapping throughout the last 2 days, but several comments indicated that a lot of that is dealing with the natural differences in needs between the commercial sector EVs and what the Department of Defense and the Army needs are. It sounds like there's a lot of appetite, or there might be an appetite for battery swapping within the Army. So definitely find an Army person here and talk to us about the needs.
Yeah, and you know, I'll just wrap up with one comment, which is there's a very strong narrative right now around charging. I'm a huge advocate for electric vehicles. If I were here 10 years ago, I would be talking about my book that I wrote called The Great Race, The Global Quest for the Car of the Future, which is talking about the fact that the whole industry was going electric. And this room of people would be looking at me saying, I don't know, electric vehicles, they seem a little bit far-fetched. I am 10 times more confident today that battery swap is going to take up a huge portion of the market going forward than I was 10 years ago that electric vehicles were an inevitability. And so, you know, I strongly encourage you to look at the fundamental assumptions of the narrative surrounding EV charging and think about how battery swapping could play an important role going forward. Thank you for your time.
Thank you.
Oh yeah, thank you.
Okay, folks, give me 2 minutes. We're going to make sure this thing's out of the way and we get set up for the next panel, and we'll introduce that here in a minute. Okay. Hey, so we've got our last panel for the day. I'm really excited that we've made it this far for the last kind of couple 3 days. One more here, and I think you'll find it extremely interesting. We've got a great group of folks coming up here. I'm going to introduce the moderator, Colonel Corey James. He is a professor of chemistry and life sciences. He's also the deputy department head at United States Military Academy. He's assistant program director for the chemical engineering program and leads an energy systems group, a team of faculty and cadet researchers developing novel chemical engineering research and optimization and process control as it relates to energy systems. Huge advocate here and great partner as we work through this event. Please welcome Corey James. All right, good job, Corey.
Can you hear me? Can you hear me? Before I bring the panel members up, I just wanted to say quickly that as a guy, you know, he told you I'm an active duty colonel, and as a guy who's been on the pointy end of the spear for 23 years now, through the last 20-something years of conflict, I have to say a big thanks to all of you for being here, first of all, and you know, really assuming some personal and professional risk in order to solve the Army's problems. I find that very important. I want to say thanks to all of you for being here to do that. It's important both for protection of our soldiers and lethality of our forces as they move into combat sooner or later. So thanks. Panel members? Oh, you're gonna take that in. So I've decided that the less I talk will be the better. You'll know here in a second why. These folks are pretty sharp. So we'll get started with just some introductions. We'll start down there on the end with Sue. Go right ahead, Sue.
Hi, everybody. I think sounds like my mic is working. I'll try to be brief, which is very difficult for me. I am the program lead for stationary storage at Argonne National Lab. I'm an electrochemist and a materials scientist, and I have had the privilege of working on energy in 4 different locations. I started at Dow Chemical. I worked and helped to put the battery program together there. So I went from a commodity company to a startup, which was A123. I was there when they went bankrupt. I went from there. I worked for the federal government. Yes, it's actually worse than you would imagine. And then I went to the Department of Energy, where I funded work in energy storage with my great colleagues. And now I'm at Argonne National Lab. So that's where I've been. But who I am is just a person, just like everybody else. Come from a very modest background, middle kid in a giant family who happened to get into science. And the reason I'm doing this is because I care about the United States, both our standard of living and our national security. And so that's what motivates me every day. Thank you.
Thanks, Sue. Bill?
Yeah, I'm Bill Sproul. I'm Vice President of Business Development at a company out in Portland called ESS Inc. And we're focused on manufacturing iron flow batteries that we can talk a little bit more about. But basically long duration, 6 to 12 hour type discharge periods using flow battery technology. So we're primarily focused on commercial, industrial, and utility scale, but there is a lot of crossover into the stationary type applications in the military, and we've dabbled in that over the years as well. So I'll leave it at that.
Thanks, Bill. Last but certainly not least, youngest on the panel.
Afternoon, Nicholas Ferry. I am in the final year of my PhD program at UT for electrical engineering, but I am also an active duty Army officer. So when I finish with that, I'll be headed to West Point to be an instructor in the Department of Electrical Engineering and Computer Science there. So what I bring is kind of meshing the academic research and electrical engineering field with my experiences in operational energy as an end user officer in the Army.
So as I stated, pretty talented group. So I'm just going to talk less, as I said. But
it's dangerous.
Yeah. But hey, folks, thanks for being here. I think that I look forward to the conversation. The conversation, just by the way, is about mobile mini grids. If you didn't see the title, wanted to briefly tell you that the focus is around what is that and how do we go about making those things, whatever they are, better. And so what I wanted to do is start off with Nick here and ask him to just frame the problem. Like, first of all, what are we talking about, and why are we talking about it?
So we are in the midst of the electrification of warfare, and it's been said many times, many different ways up here, but it cannot be said enough that is what's happening. Every demand for the soldier is becoming electrified more and more. We're having to push more and more electrical energy further and further for the individual soldier to use at the very front lines, where that in the past that hasn't been the case. So looking at that and talking about mobile mini grids, there's really 5 types of Army microgrids. 2 are not mobile, so we won't talk about them. So the largest mobile microgrid mini in the Army right now is the battalion and brigade command post from a brigade combat team. These are your forces who are out there actually engaging with the enemy, and their command posts essentially exist as these mobile, permanently islanded microgrids. And they're powered solely by one diesel generator. They have a radial distribution system that consists of essentially extension cords, okay? Trying to get people away from using the convenience receptacle on the generator, but they actually hook it up to the lugs in the generator, and it's a radial distribution system, but that's how we distribute our power for those mobile command posts, and anyone who's chuckling has actually seen one. Okay. So there's no resilience in that system, right? It's entirely dependent on diesel fuel for power and energy production because there's no energy storage systems. There's no renewable integration today at scale for those systems, which could offset diesel fuel consumption. And there's also no redundancy in the distribution system. We're talking a purely radial system as opposed to a mesh system, which has some redundancy in case you lose distribution lines. Okay, shrinking that down slightly smaller, we have our next grid, and that's the vehicle-based microgrid. And we need to start thinking of our vehicles as microgrids. In World War II, the Jeep carried you to the battlefield. The truck carried you to the battlefield, and that was it. Maybe it held a bigger weapon than you could hold. Today, these vehicles are not only holding our troops and bigger weapons, they're also holding a suite of electronics and other things that do incredible things for our soldiers. They're also a place for our soldiers to charge the individual components of their systems that they use when they're not in the vehicle, because they often don't fight at large in the vehicle. Okay, so these vehicles need to start being think of as smaller nanogrids as well, or microgrids for that term. And then lastly, and perhaps most importantly, you need to start thinking about the individual soldier as a mobile mini pico or nanogrid, depending on which term you want to use. Right? And there's a lot of work with conformal wearable batteries where we're starting to think about how do we give the soldier a centralized hub of energy that they can use to distribute to all the various sensors and weapons and imaging and communication gear that they carry. And if we do that, and we start thinking about it as a grid at each of these levels, we have to start thinking about, well, how do they integrate? So after an attack on an objective, can that soldier cross-level ammo and water? If anyone here is a soldier, they know that you do that. Some people drink more, some people shoot more than others. But why can't they cross-level energy? Why can't we plug together and share energy between 2 batteries that a soldier's wearing? Mm-hmm. And now, if we start talking about hybrid vehicles and electric combat vehicles, can we do the same thing with vehicles? Can 2 vehicles come together to form a mobile mini grid? Okay. And then the same thing with our command posts. So command posts are the seed for which we will use as a model to charge hybrid and electric combat vehicles, right? It's the best thing we have today. It's the closest thing we have is those command posts. So an overview of an aspirational mobile mini grids.
Well done. Well done. So you mentioned the word battery. Imagine that. So since Bill does this kind of work, I want to ask him what challenges do we face to take these, the technology that you work with or other technologies as well, but some sort of robust storage capacity and place that into a tactical environment? What are the challenges associated with that?
There's a lot of challenges, and I'll preface it with keying off of what you were saying, Nick. The large stationary batteries like we build, flow batteries, are really addressing the command level. Temporary base setup for a period of time, may have to move it from time to time, but not vehicle, not soldier type applications. We've gotten involved a little bit in demonstrating the iron flow battery in that application. And the challenges really revolve around the logistics of getting a battery to the site. Example, lithium ion, very heavy once you have a container filled with lithium ion, hard to move that, has a little bit of safety risk that's been touched on before, and it degrades over time. So you're not going to be using that as a 25-year asset that you move around the theaters. So that's one aspect. What we've kind of focused in on is trying to minimize the amount of fuel that has to be moved forward, increase the efficiency of that 60 kilowatt diesel genset that's been talked about. One of the things that we learned in a project we have been doing and will continue to do with the Army Corps of Engineers is a lot of those 60 kilowatt gensets are only running at 5 or 10 kW most of the time. And that's obviously not the most efficient way to run a diesel genset. So that just means that you're bringing a lot more fuel forward to feed that bigger than you need genset normally. By putting a long duration storage in, maybe coupling it with solar so that you've got on-site generation that you can leverage, you can dramatically reduce the use of that diesel genset because those 5 to 10 kilowatt nominal loads can be covered for a long period of time by an iron flow battery or any kind of battery that you bring forward. You can call on the genset to recharge you very quickly. You can recharge at 60 kW efficiently using the genset and then carry the load the rest of the day. So that I see as a significant use of a stationary type battery.
Okay.
So I'll leave it at that.
Thanks, Bill. Thanks.
Yeah.
So, Sue, I wanted you to touch on, if you would like, or just ask you the question.
He's going dangerous ground right away.
Give her a time limit, you know.
Yeah.
I wanted to ask you the question. Are there, you know, Bill talked about a technical challenge that we're kind of all aware of. But what other challenges do we have in the space with mobile mini grids and trying to solve this problem? Can you expand on that from your perspective?
Sure. I'll give you the perspective that's hitting me as I come here right here today. So I think I've been trying to I'm going to make 3 points. First of all, let me just preface it by saying I come from a national lab, which is a place where all of the taxpayers send tons of money to make like your science dreams come true. Okay, I mean, it's really an incredible place to be, but the government invests in national labs because that's where we do like really leading edge work, and that's where we're supposed to be pushing the bar higher and higher and higher, and that's a great thing. So I'm going to talk from that perspective because that's part of what my job is right now, rather than being a different part in the ecosystem. But when we're there, I get a view of what could be. So I would say that when I come here, I'm very saddened because I know that we can solve this problem because we are doing it at a much more complicated level at our national lab right now. For example, I work with a bunch of IEEE guys who are trying to integrate the entire US system, transmission lines with natural gas and coal and electricity, and they're trying to figure out how to do agent-based modeling for how do we build out our charging infrastructure. So at a much more complex and complicated way, these very problems are being addressed right now. And there are tools that we have where we could sit down with you and you say, like, well, that's just like, you know, when you put Iowa with Montana or something like that. So by analogy, I can tell you that these thoughts have been worked through and these things can be linked together. So it does exist. And I know it does, but I'm also know that how do we get that word out to folks that it exists? And we are not, there's no point in us generating knowledge if it's not used. So we need to get that information out and get it into your hands. So number one, the project is very doable at the very complicated level, and we're here to help. Okay, so that's the first thing. The second thing is that from where I sit as well, if I think about what this needs to look like 10, 15, or 20 years from now, based on what I know and these stories I've been hearing for the last 20 years, we can actually get 7 to 8 years down the road with the tools that we have right now. You don't have to invent anything new. You just got to take what we've got and bring it together, and we can get a really long way down that road. That's both in terms of hardware and in terms of software. And if it's just like, do we do inductive power transfer instead of like worrying about wires, or how are we going to do that? And what do you have to do to like not explode something when you're doing inductive power transfer? So we have all these things, but I think part of the problem is that the ecosystem is very fragmented right now. I think these bits and pieces of information are here and there. And I was going to say, in the Venn diagram, there's not enough overlap. As a matter of fact, I think the balls are going across each other and whatever. And that's just because there's so much complexity and we don't know how to interact and communicate with each other. I told in my breakout group yesterday, I said, like, we could do this for you. And it's like, we're going to use machine learning, and hey, do it. And it's like that communication didn't really work when I presented something. And then I had a really wonderful conversation with Ashley this morning, and it's like it's starting to communicate. So I think what we have is the problem can be solved. The bits and pieces can get us there in 5, 6, 7, or 8 years, so much better than we were before. But I think that the issue, a large part of the issue we have, is bringing these different bits and pieces of information together. And now when it comes to what are exactly the gaps on that, I don't know necessarily what it is. I think it's easier when I don't explain it perhaps clearly enough, or can I help you to explain it to someone else? How do we solve that problem? That's something that we have to work on together, though, because I can only see it where I sit, and I'm a bit mystified, but I know it's very real, okay? And I know that the groups we are not cohesive as an ecosystem, okay?
So you're saying that we do have the intellectual capital in place. So
yes.
So we have the folks to do the job throughout this room, all different flavors.
Yes.
So you think that exists? We just need to synchronize our efforts a little better as a nation, as a community. And I'm asked, that's a question.
With one, I would only change your sentence, one word in your sentence. I wouldn't say we just need to synchronize. I say we need to synchronize, because just does not give it justice, if you pardon that. I just made a play. Fair. Anyway, I mean, there is obviously a very significant barrier here. Okay. So the communication is not going where it is. What do I need to do to help you to be successful? We've got a supercomputer. I was telling somebody about at Argonne National Lab, we have a supercomputer that we just turned it on. It's going to consume more power than the whole campus of 3,500 people does right now. The amount of power that it consumes is enough to provide electricity for a town of 800,000 people, okay? So I'm using that, and I'm not trying to impress you. I'm just trying to say this is an example of the resources that the United States of America and U.S. taxpayers have invested in. How do we get that to you, okay? So that is what I think when I see this here today, I see that. And as I've been in these different roles, I can see that in each of the places I was in, I only saw part of the problem.
Okay. Well,
so me too.
Let's think through another problem here together. And I open it up to all three of you, just take stabs at it. But, let's think through a 15-year plan. Let's think about what, if you were talking to you are talking to this audience, but, you want to impress upon them that we should really think about some key milestones in the next 15 years to solve the problem. What would those be? What do we need in the next year? What do we need 3 years from now? What do we need? What's going to take 15 years? What is that?
Okay. So
anybody?
You can go first.
The first thing is more power. Is the answer to every single question you just asked. It's more power. There's always going to be more and more demand, and it's going to go more and more forward. Whether we're talking about hybrid or electric vehicles or directed energy weapons or more individual soldier power demand from things like IVAS or the new optic we just decided to use, which is great, but requires power where the old one didn't. it's always going to be more power. And it's going to be more power 15 years from now and more power 30 years from now. It's always going to be more power, more forward. The first milestone I would propose is an energy storage system integration at the lowest level. Even if that's just a battery pack that rides in a combat vehicle that soldiers can come in and connect to, even if that's just a battery pack that goes with your battalion and brigade command post to keep your servers up when you move from one spot to another, because by the way, they turn all their servers and computers off, move and turn them all back on again, which is great if anyone's a computer person. They really like it when you do that to them. Simple things like that can make a huge difference. It also allows us, can be done today, to Susan's point, integrating energy storage with diesel so that our diesel only ever runs at 100% of its rated power, its most fuel efficient operating point, and that energy storage is there. Not only does it provide thermal signature management and acoustic signature management, it also improves improved fuel economy.
Okay.
Those are the first two milestones, I would say.
All right. Bill, do you agree with that?
I agree with that. I'm gonna go a different direction. If you're talking what's needed to get us 5-15 years down the road is really a leadership strategic vision of where it has to be. And I'm kind of listening to what Susan's saying, but there's all these assets out there. We're doing a lot of stuff on the commercial side. You guys are doing a lot of stuff in the lab. There's a lot of needs out there that are disparate and not cohesive. I think probably the biggest thing, no question, technically you need more power as we go forward, but somebody's got to put that vision together as to what it looks like 15 years from now and pull it back to these are the things we have to do in the next couple of years to get to that point. And I think from any organization, whether it be commercial or military, has to have that strategic leadership to bring all those disparate capabilities together to get there. So that's what comes to my mind first in this situation.
Yeah, so we're the operational energy guys writing that. Way back there, sir. They're writing the strategy. Yeah, so that's going to be out. What was it? What's the timeline on that? It's within a year, I think. That was the first day of the conference, so I got a little fuzzy since then, but it's within the year. And so, to your point, Bill, I think that's a step in the right direction in order to have a document that says that we will do these things over a period of time. I forget what their timeline was, whether it's 15 or 15's my timeline, but whatever it is, I think it goes out a little longer than that. But that's a great start, I think. But I think we could have some more direction is what you're asking for, right? Some directed task that, hey, by this date, we need this thing without fail turned over to our soldiers. Is that what you're saying, Bill?
Yeah, and down to the R&D level through the commercial COTS type of systems. What can I convert over to a military use?
Right.
That kind of thing. And there's plenty of capability to get there, I think.
Okay. Sue, are you?
Yeah, no, I'm always trying to keep myself to 3 points I want to make. First of all, my first point is I want to echo what Bill said. Okay. Because you need leadership. I told you that this is all possible, and I could have made that sentence 5 or 10 years ago. Okay. So we have to have a forcing function. The reason China is eating our shorts is because they have a document called China 2025. And you know what? They don't just write the document, they actually do it. Okay. So you have to have a plan, but you have to do the plan. And that comes down to leadership. And I think my comment on leadership is consensus is not leadership. Okay. Somebody has to make a decision. You were just going to go do this. And you have to say, it's not going to be perfect. We're not going to do it when it's perfect. We're going to make our troops a living lab, and we're going to make it. We're going to have some sort of a reward system. So when things get all messed up, nobody gets punished. It's like, okay, what did we learn? And let's go do it. So we have to decide that we're going to move forward and that it's not going to be perfect. And we're just going to do it. And that's it, period. And so you have to anoint somebody to be a leader, and that just has to happen. So I agree with Bill, because no matter how great a plan, if you don't have a leader and you don't, and it's just a plan, it's like, why even do it? So That's the first thing. My hat's off to you. And think of China, and think about what we just heard about, like car swapping instead of fast charging. So that's like an example. So that's the first thing. But once you decide you want to do it, if I say like 2 cornerstones of this, is I believe we also need to have those very driven leaders are going to say these systems are all going to be interoperable, or we aren't going to have them. So if you want to supply to the government, you got to have these connectors, and it's got to have these characteristics. And if you aren't going to do them, I don't care what your excuse is, go away, and I don't even want to hear you. Because again, like then I keep talking about Ashley, this panel that I was in with her yesterday, I think it was Stephen over there, they were talking about how all these batteries are laying around and they aren't used. And so if you're saying you don't have enough energy, I would say, well, let's first of all, let's count up how much of the energy you've purchased is sitting unused. Because if it's 10%, which is, I'm thinking 10% might even be a number, you've actually got 10x more power than you thought you have. So let's say interoperable, and if you have it, you're going to use it. Because that's, I mean, that just think of all the problems you solve there. And then the second one is because I am at this place that I'm not a data scientist, but I work with them. If you have the ability, and we have some tools right now, if you use AI and machine learning, you can in real time understand, where is that soldier, who is coming up short, who likes to use all their energy, and who is cautious and doesn't use it, and tell this guy, go over there and stand with this person. I said, guy, pardon me. Tell this person over here, you go stand with this person over here, and you transfer some energy, and you've got like 20 minutes to do it. So we can use data sciences to improve what we have. Okay, so those two things, interoperability and data sciences, that's all about improving our efficiency. And we don't even know how good we could be right now. I think we could be a lot better than we are, okay? And I would say it's because the battery community is on its own fragmented. It's not just this group here, that data sciences has escaped the battery and the energy community for longer than anyone else. Think about like the pharmaceutical, think about like every time you try to read your newspaper and an ad comes up of something that you looked at online 2 days ago. I mean, these things all exist right now. And the reason it's not being used is just because the information sits in these fragmented groups, okay? So we can bring them together. I think we can do a lot better. Okay,
so within that 15-year plan, we're writing this as we go here. You just talked this was my follow-on question to all of you, and maybe Sue just said it. We'll see. Maybe you guys disagree. Is that the real big disruptive technology over the next 15 years or so? Data science, AI, ML, which, that's not anything new, but maybe in terms of mini microgrids and the way the Army uses that stuff, is it disruptive in terms of what we need it to do? Is that it, or is it something else that's going to really, because we talked about generators, making those better. We talked about other things, using what we have and just making that better connection, better, usage, smarter. But then you said something that is disruptive. And so is that it? Or
let me just say this. At Argonne, we are using machine learning and AI right now to run power flows on very, very super complex grids in real time. Now, you take that model, you have a different level of complexity, okay? But what I'm saying is these things are being done on power flows right now today, and that those learnings can seed the description that we had as we started.
Gentlemen, you agree? Disagree?
So I think in terms of, if you consider the individual soldier a mobile mini grid, the disruptive technology there is what everyone's been asking for the entire time we've been here. It's high density energy storage that's safe for the soldier to wear. And what that gets us is Iron Man suits, right? That's what everyone wants. Everyone wants an Iron Man suit. That's what every soldier wants, right? But that's where we're headed, right? We want to give the soldier as much energy so we can give them bigger, more powerful weapons, bigger, more powerful sensors, more edge computing, and be safe in the process, and also more armor, because if they had a machine walk for them, they wouldn't have to walk, right? So in my opinion, in the next 15 years, the disruptive technology for mini grids is individual power storage that's both safe and energy dense. At the command post mini grid and the vehicle mini grid level, there's no disruptive innovation needed to do what we're kind of talking about here and making those effective grids. The Army has its TMS protocol developed by C5ISR, which is well on its way to becoming a standard. And when that's adopted by industry, now you have the ability for all these disparate, his battery to be able to talk to an amps produced generator, to be able to talk to a solar inverter bought by some third company, all working cooperatively with some central control. All that's achievable today.
Yeah, just picking up on that, it's being implemented today on commercial microgrids. We're in a microgrid down in San Diego that's a utility-owned microgrid, solar, flow battery. It's there for wildfire mitigation. So in California, when the weather conditions are ripe for wildfire, heat and wind, they'll shut down distribution grids. So whole communities, whole areas go out of, don't have a grid anymore. So one of the strategies is to put in a smart microgrid that's resilient, can go multiple days off a solar battery, backing up critical infrastructure. And that's what this one is going to be doing. But it's got a control system in there that can not only keep track of what the weather conditions are and anticipate situations, but it also, when it's not needed for that, can do a multitude of other use cases, do energy shifting to the peak in the evening in Southern California from the solar, do ancillary services to the CAISO wholesale market. So there's a lot of smarts that are in these microgrid control systems that could be adapted to any one of these military microgrid type applications and be able to feed off of your.
Great. Yeah.
So you bring up controls. That's near and dear to my heart. But, you know, we're also concerned about how energy, and Sue brought this up, not only at the battery kind of grid level, but how, you know, she spoke about awareness of knowing that the soldier's standing over there without the assets to go another energy assets to go another hour in combat. So right. Sue wants something that's going to tell that soldier that he needs to go stand by this other soldier, you know, or, you know, as a simple example. Does that exist? I mean, are we working on that, or what do you even mean by that?
Well, at Argonne, we have something which is similar to it. I don't know, like if it's a drop in, but we have, see, one of the differences between stationary storage and the soldier power is that soldier power is used when you have these high energy density batteries. Their capacity tends to fall off with life more than, I mean, the miracle, I shouldn't say it's a miracle because it's real, of ESS is that their capacity doesn't drop off. But the types of batteries that you put on soldiers, they drop off, the capacity drops off with use, and the profile of that is very path dependent. So one of the things that we worked on is how do you send a pulse to a cell, or either a cell or a module? How do you send a pulse to it and know how charged it is, what is it, how healthy is it, and how can you use it going forward? So that is a thing that we could add to that situation there that perhaps doesn't occur right now. So the background good news is we're very close to having all the bits and pieces. It's just maybe some of the algorithms could be a little better, because it sounds like you've got standardization for interoperability, which I didn't know. And so that is a thing that could help that scenario right there. And then for transmission systems, it sounds like I didn't realize how sophisticated they were. But I mean, for the U.S. system, we've got a lot of tools. So we can take the algorithms that we have and just drop it into the system you have, maybe upgrade it a little bit, make it a little fancier, a little more predictive, bring in some economics in that.
Yeah, I guess I'd quickly just look at the soldier as a system that you're monitoring out in the field.
Yeah.
Just like the microgrid I just talked about, it monitors every one of those iron flow batteries. It monitors the solar system. monitors what the weather's going to be, and optimizes, makes decisions on how best to utilize all those assets, and actually communicates to them and tells the battery that it's going to be cloudy this afternoon. I want you at full state of charge.
Yeah.
That kind of thing.
So
if
go
I could
ahead.
answer.
No,
So
go right ahead.
In the Army, this will require a cultural revolution to get at what you're talking about.
We don't like those.
No, and they're very, very much not appreciated. So in the National Training Center of California, some of you who are shaking your head or hanging your head right now have been there. It's a wonderful place. If you get the opportunity, you should not go. But it's where brigade-sized combat teams, which is the main combat force of the U.S. Army, go, and they conduct an exercise against a team that lives there and knows the terrain really well, and just absolutely destroys them as part of a developmental process. So it's sort of, in today's Army, the ultimate test of your leadership and your training and your equipment. So when you're there, the question asked to you daily as you send up your log logistics report is, how much fuel do you want? And then the next day they ask, how much fuel do you want today? How many pallets of batteries do you want today? How much more fuel do you want the next day? Right? Forecast your fuel for the next day. No one ever asks the question, what did you do with the 3,000 gallons of fuel I gave you yesterday? Right? How many miles were you able to move? Right? Do you really need this? How many 5-gallon fuel cans are in the back of your truck that you're just holding on to for later? We don't do a good job, and because it's not incentivized and it's not important, of actually looking at how we're using that energy and then reporting that back up to gather that data to allow some sort of high-level data analytics, some sort of machine learning to look at that and say, okay, this is where we can invest to improve our energy consumption, because there's just no culture of even being accountable for it.
Sort of a cultural problem in the Army
when it comes to energy.
Yeah, and I do agree with that based on personal experience. And that's part of what drove, I will interject here just a little bit because I have some very passionate things to say about this. You know, the Army made some mistakes in terms of being inefficient at the unit level, and that's what Nick's talking about. And we just didn't have a good plan in place to ensure that folks were being more efficient, which would have kept soldiers off the road. We were trying to win the fight, and I understand all that. I was in the big middle of it, but they did put soldiers on the road, and in some cases got them hurt or killed. And so that's part of this discussion, is I'm trying to pull out of these folks, what is it that we can do to not put people on the road, or in the air for that matter. Air's a little safer, but as we know from watching CNN for 20 years, the road is not a good place to be. When the enemy knows that we are craving JP8 24 hours a day. We cannot live without it. So I want to just kind of ask you this one more time. I'm going to move on to a different topic. Is there, you know, throughout the 3 days here, I've heard folks say the term, we're going to turn that on its head. You know, we're going to flip that on its head. Is there anything with respect to mobile mini grids we should just flip it on its head, drop it? It doesn't work. We're doing it wrong. I mean, maybe it's this that we just talked about. We clearly are not aware of what we're using. I don't know. I don't want to put words in your mouth. I want you to answer the question. But do we need to flip something on its head and go back to the drawing board totally? I mean, Sue talked about, hey, let's use a lot of stuff we have. What do we not need to use? What is broke?
well, okay.
Go ahead.
Can I just say this?
Yeah, either of you. It doesn't matter.
So there is no polite way to say this. It's an attitude that you don't have to know this. We should say, like, you have to know this. If you have people have to be physically trained in order to do these jobs, and I know that I couldn't pass those tests. I don't know if I ever could. But I mean, we should put training and an expectation of sophistication as part of the training. If you want to, like, leave something behind, leave it behind that this is optional. I think you need to train, find ways and to understand who are the people that are going to use these and make these things very user-friendly to them, so that it's second nature, that there will be an expectation in the future that, yeah, like I can go run, 7 miles at an 8-minute mile. And by the way, I can go hook that up and tell you what's wrong with it in like I can figure it out in 60 seconds and go fix it. I think that needs to be an expectation that we need. If when we set it, though, you have to train people for it, right? But I think that is so doable, because think of how we use our cell phones right now. Who would imagine, like years ago, 8 years ago, that we'd be using our cell phones the way we are right now? Or I was just on a bus, and a 1-year-old took his mother's cell phone and he swiped it and started like looking at it. I mean, that person is growing up learning how to do that. Okay, so I think that we can do it. It's actually not that hard. We just have to say, okay, we're going to spend time to make that level of competency something we're going to push and we're going to achieve.
Real quick. Oh, go ahead.
If I could just build on that to more direct Army application. Does anyone have any idea who manages the diesel generator for a battalion and a brigade? Like, who's the person who does that? No, I mean, not in the sense of the PEO. I mean, the sense in the person of the soldier in the unit who's responsible for understanding how that device works, right? It's the 91 Delta, right? The generator mechanic is ultimately the person who runs that device, right? Do they have the ear of the battalion XO or the battalion sergeant major? Mm-hmm. They don't. Their job is to fix the generator. Okay, that's how they're used. That may not be how they're trained, but I'm telling you in practical applications how they're used. So to your point is educating our force and developing some sort of energy leadership beyond the junior enlisted mechanic level could have a very big impact to understand these technologies, understand the advantage of these technologies, and understand the setup they're going. And the second thing, very quickly, sir, is what I said in the beginning. If we want to turn something on our head, let's turn this grid-centric view on its head. Let's look at the soldier as a grid that can come together with other soldiers and form a larger grid. Let's look at vehicles as our own individual nanogrids, and let's look at command posts at the battalion and brigade level as individual grids. So theoretically, our brigade, if it's in the rear area, every little soldier, all the way up to the brigade headquarters, are all on one power network, which can be super efficient compared to them when they're split apart. And that's compatible with multi-domain operations.
Awesome. Let me shift gears a little bit and tie this back into the commercial sector, since we have some commercial folks in the room. Brantz has asked a question. So what are the driving forces and use cases for mobile mini grids on the commercial side? I think, how do you, what I'm understanding by that question is, could it plug and play on both sides of the fence? Something that's maybe already being used, could it be quickly adapted, or vice versa? And you've talked a little bit about that, Bill, going from commercial side to, especially with your flow batteries, going from commercial side to military. There's some challenges there, right?
Well, there's certainly challenges in ruggedizing something that, we're going to go put it on a site in San Diego County and it's going to sit there for 25 years versus I'm going to throw it on underneath a helicopter or on a truck bed going across the desert or something like that. You have to worry about the ruggedization of those commercial assets. Yeah, I think that's probably one of the big things. What I think, just going back to the last question, the piece that I think needs to be at a higher priority is worrying about the efficiency of the assets that we do use. You touched on the diesel genset, use that only in an efficient mode, bring in storage or some way to enable that. But I think and I'm a layman when it comes to military operations, but my understanding is that the last thing that strategically they worry about is how many tanker trucks they have to bring forward. They just know they need those there when they're running low. So shifting the emphasis to how efficiently can I use the assets I have forward and trying to minimize that makes a lot of sense to me.
Yeah, are those motivators for what the Army needs? Are they the same as like in the oil patch or Arctic or some place where you're remote, you need power, you probably need to be very efficient because the next load of energy is coming not tomorrow, it's coming later. So those sorts of things, as I'm reading this question and thinking through it, I could see, I know why Brantz is asking that question. And You know, are those two things really similar in certain industries in certain parts of the world? You know, we're doing work in remote, you know, parts of Australia or Africa or places like that. Does that apply? Would it be similar?
In my opinion, absolutely. Any place you're in an austere environment and you need reliable electric power, and you're going to use hydrocarbon-based fuel, or since we're talking microgrids, any collection of fuels, right, for your electrical power generation, it makes sense to have some sort of mobile mini grid. And it may not be as mobile as moving every 24 hours like an Army command post would, but if you move every few months, it's not all that different.
Yeah, here's a good one. Real quick in the last, you were rapid fire here from the iPad. There's a couple good ones popping in. You know, how do these potential energy solutions sync in with our allies? That's a big issue we always have. If you join operations with even some of our sister services and you know, go work with Marines, Navy, Air Force, not everything is always compatible, to include our radios sometimes, which is unfortunate. But you know, I see that. Got a reaction. But then you go work with, you know, I've done a lot of work with, you know, Slovenians and I was in Europe for a while, different countries in Europe, and, you know, they do business a whole lot different. And so that's a huge consideration. Maybe you don't have the answer, but it is a huge consideration when you are parked remotely with, you know, the Polish army on the border of Ukraine for a long period of time, which apparently is happening as we speak. Are those things compatible? Can we be efficient together, or is it just the United States military doing their thing and our allies? I don't know if we have an answer to that. Do you?
I'll take a stab.
Yeah, I'll take a stab.
So for the most part, the AMPS generator is extremely capable of producing power to what our NATO allies can produce and consume. And not only that, but most of our devices are electronic in nature. They end up using DC as the end use case anyways. And that's true for electric combat vehicles and also for directed energy weapons, which kind of wanted to make the point is the next iteration of grid, we need to reconsider, are we using AC as a transmission medium? Why? We're going 100 feet, right? Let's raise the voltage and use DC. Right. And then, by the way, if we have the same voltage, you don't have to worry about frequency with DC for my non-power people in there. So the Polish DC at 600 volts is exactly the same as the American DC at 600 volts, whereas our AC would be at 2 different frequencies and it would cause really bad things to happen if we put them together.
So the problem may exist on our end.
Well, we could
be better.
There's just more of us, sir, so it's their problem.
I can say that, again, from where I work, there are ever increasing heightened exchanges with our allies on energy storage. Like we do things with the UK, and then we've got things going with several of the groups in NATO in terms of just like raising all of these allies to a similar level. And so I think that something like the concepts of interoperability and standardization, that falls right into the fact that already the paradigm of sharing and increasing, like in this case, it's for a larger market, so you have greater supply chain leverage. But I think in terms of defense, it's the same thing. Certainly the crisis that's happening right now in Eastern Europe, if they didn't think so 3 or 4 months ago, they think so now. So the groundwork is there.
Yeah, I liked your comment about DC power because really the only reason you might want to have AC is because you got generators out there. If you're less dependent on generators, more dependent on renewable, solar, batteries, etc., you're more efficient being DC. So that and there's easy interoperability on a DC power grid. We're building for Europe and Australia and South America right now. So we really don't change the configuration of our battery for that.
Awesome. Well, listen, I wanted to once again thank the panel. A great conversation. If you would give them a round of applause. I'm certainly glad I was sitting in this chair and not those. They did a great job. I think we would all agree on that. Thank you very much. I appreciate your thoughtful comments, and I look forward to future, collaboration and interaction with you. So thanks. Nick, it's all you.
Thank you.
Okay. Hey, so we've made it all the way through the panels today. We do have breakouts still to do, and I think they're going to be very valuable, especially in some of the topics that we have coming up. I do want to be able to just say a couple quick closing comments because we won't come back in here after we're done with the breakouts. But please, for the breakouts themselves, if you're assigned, please, that'd be great if you can be there and be in the right breakout. If you're not assigned a breakout and you'd like to go to those places that you want from a location standpoint. We have 3 breakout rooms here on the bottom floor, and then the 4th and 5th floor, or the 5th and 8th floor as well. Like I said, the first day, very complicated. You're welcome. But hopefully everyone had a fantastic time for these last 3 days, or if you just made it for today as well. I think you can definitely be on the lookout for some of our follow-up correspondence from the Vertex team. We definitely want to continue the conversation, but also deliver on what we've been receiving from folks, both industry and Army, and share as much as we can with the group that are part of our network, whether you're here in person or virtually. I am just an active duty armor officer, but so my equities definitely lie in the ability to sustain tanks and Bradleys and fight, and we have to win. So just from that perspective, I'm just a subject matter enthusiast, not an expert like yourselves. But what I'm watching here and what I've seen, I'm cautiously optimistic that we can do better here, and we can share well and actually make progress collaboratively. So I'm excited about that opportunity. I'm excited about the connections that were made, and I would love to get some feedback as well from folks on how we could do better in the future, whether that's energy or anything else that Army Futures Command's trying to do. Again, I'm here through this afternoon. Thank you so much. Hope you had a great time, and let's close out well. Thanks so much.